Okay, yes, already. So today we're going to discuss round 2, linear regression. And although I'm pretty sure that majority of people familiar with the linear functions or regressions, how they called, let's do some brief recap. So linear functions are the functions of the form y equals b plus wx. And in this formulation, we have a parameters of this function, b, bias, or it's called also intercept or y-intercept, and w, which is called slope, also referred to rise over run, weight, or coefficient. Then the variable x is what we call feature in this course. But if you are from some other fields, you may heard also predictor, independent variable, and the y variable we refer as label, or the outcome response variable or dependent variable. So the regression problems are the problems where we have y as a continuous variable and real valued one. So it's basically float point numbers. Here you can see the graph, some example of a graph of linear function. And the exact equation for this linear function is y equals 3 plus 0.5x. So let's see what are those parameters of this function and what they actually reflecting. So in this case, we have 3 as a bias or intercept, or also called y-intercept, and the slope is 0.5. So here you can see that this linear function intercepts or crosses the y-axis at one point and the x-axis in another point. So this cross point with the y-axis is actually this bias or intercept or y-intercept. And from the graph, you can see that it's indeed 3. And x-intercept is a point where the y is equal to 0, and in this case, it's -6. So the slope is reflecting how the function is changes, how fast the function is changing, or how steep this line is. It's also, for example, in school, very often referred to as rise over run. And so you can compute the slope by using this rise over run formulation. So what does it mean? Well, you need to choose 2 points on the line. For example, we can choose the x-intercept point and the y-intercept point. The x-intercept point has coordinates -6, 0, and the y-intercept has a coordinates 0, 3. So we need to compute the difference between the y coordinates and x coordinates of these 2 points, and then compute the ratio of those. And this ratio is 0.5, and actually it's the same as this slope that in the equation. So it just shows how steep this linear function is. We call the slope positive if this weight or coefficient is a positive number. And basically it means when the x is changing or getting bigger, larger, then the y is also getting larger. If this coefficient is negative, this is a negative slope, this blue line, and it means that when the x is growing larger, then the y is going smaller. So there's a negative relation between y and x. And if the slope is 0, it means that it doesn't matter how x is changing, the y, the response variable, will be constant. So it basically means that there is no relation between the x and the y. Previous equation was written for very simple case for one data point, where data point characterized with one feature. Usually we have more complex data. We have many features. So in this case, we can write out the equation for the linear predictor as y equals interceptor bias plus sum of the product between the corresponding weights and the features. Or more concisely, we also can write it in the vector form, where W is a vector of coefficients and X is vector of features. And basically, we are computing the inner product of transpose of vector W with X. Yes, and I forgot to note that the regression, the linear regression with many features, also referred as a multiple linear regression. And we often want to formulate this multiple linear regression in the matrix form, where we can stack all the equations for each data point in a matrix form. So let's assume that if we have m data points, then our equation is going to be vector of labels y equals b plus matrix multiplication X big and W. And the X here is a feature matrix. So it's a 2D array where each row of the matrix will correspond to one data point and each column will correspond to one feature. And then we perform matrix multiplication with the vector W of shape N1, and the resulting vector going to be of shape M1, which is the same as shape of the label vector. So it's a more concise way to formulate multiple linear regression for all data points. Now, when we decided how to write up and formulate our hypothesis space of these linear predictors, we need to formulate what is our goal or what is our objective. Well, obviously, what we want to do, we want to get good predictions. And what does it mean formally is that we want to find a hypothesis or model of the form h of x, and h in this case chosen because of its stands for hypothesis. H of x equals b plus wx. And we want this hypothesis to be such that the predicted values, which are often referred to y hat, will be very close to ground truth or the labels y. Just a quick note that this hat notation is usually used when we talk about some estimates of some variable or some parameter. So in this case, this y hat in our course usually mean predictions. So we want such a linear function, such a linear regressor that would give us predictions that are very close to labels. And this difference between prediction and the true label is called prediction error, or in other fields, for example, in statistics, it's also referred as residual. Here you can see a familiar plot. You saw them already in the round 2 notebook. And here we can see the data points in the blue, linear predictor in black, this black line. Predicted labels are the green dots, and the prediction error or residual are these red lines. So the objective that we have, we want these green dots be as close as possible to the blue dots. So how we can solve this kind of problem? Well, we need to formulate what kind of loss function we're going to use. And just to remind, maybe I wasn't stating it very clearly, but we use loss function not only to estimate the discrepancy between the prediction and the true label, but also we use the loss function to guide the optimization algorithm towards the optimal parameters of the model. So it has two very important tasks. So very natural and logical thing to suggest, of course, let's try to minimize this prediction error. And to be more precise, the absolute value of the prediction error, y minus y hat. If we formulate the problem like this, then it basically means that we are using mean absolute error as a loss. Here you can see the formulation of this mean absolute error, basically just an average of the absolute value of prediction error for all data points. And below, there is a graph of the function of this type. And the things that you need to note here, that it's kind of a V-shaped, and there is this very weird point here, like a corner point. And these kind of functions are called non-smooth because they are have these sharp corners or angles. And we will discuss later what are the consequences of this kind of functions, of using this kind of functions. Another option is to try to minimize the squared prediction error instead of absolute value of prediction error. And this amounts to using mean squared error loss. Here again, you can see the formulation of the mean square error, and below it's a graph of this kind of function. And in contrast to the previous one, you can see that this one is very smooth, and it doesn't have any kind of sharp points in any of the x values. So if we compare these two kind of loss function, mean absolute error and mean square error, we'll find a few important differences. Mean absolute error is more robust to outliers than the square error. I will skip the derivation of the statement or the kind of reasons why this is true. But if you're interested, I can send you some links for the derivations and more thorough explanations. So then, as we noted, the mean absolute error is non-smooth function. It means that it's non-differentiable at this corner point. And the consequences of it is that we cannot apply very efficient tools and algorithm for optimization of this loss function. So it's more difficult to work with this kind of function. In contrast, mean square error is smooth and easy to optimize. And one more difference is that mean absolute error has no analytical solution or a closed form solution, but mean square error has the closed form solution, which is called ordinary least squares or also normal equations. In your notebook, you've been presented with another type of the loss, which is sort of brings the best from these two loss functions. It consists of two parts, where one part we use the loss function that is practically the mean squared error function, and another part is looks like the mean absolute error loss. So how does it work? It's illustrated in this figure. So we need to choose some kind of threshold epsilon, and dependent on this threshold epsilon, we can define two regions of the parameters. So those data points which are in the region that are closed by this threshold, those are going to be known outliers. And we use mean square error to compute the loss for these data points. For the data points that are considered outliers, and it depends on the parameter epsilons, for these kind of data points, we're going to apply the absolute error, and this is an outlier region. And the result of combining these two parts is the function, the loss function, that is more robust to outliers, but which is also easier to optimize. Here I have another figure which explains the difference between different losses. So from the left, you can see two linear predictors. So this one is a predictor 1. And this predictor 1 tries to fit the data points. The data points are these black dots and one outlier, the cross. So this predictor fits perfectly to all data points except the outliers. So for these data points, the difference between the prediction and the true label is 0. Now here we have a prediction number 2. And the predictor number 2 has a prediction error for the outlier a bit smaller than predictor number 1, but it also have a larger prediction error for the other data points. So now let's take these two predictors and use different losses, absolute loss, squared loss, and Huber loss. And we'll use these losses to estimate the quality of these predictors. So on these subplots, on the x-axis, we have data points. So this is data point 1, 2, 3, 4, 5, etc. And on the y-axis, this is loss. In this case, it's absolute loss for each data point. And loss for predictor number 1 is depicted in black, and the loss for predictor number 2 is depicted in red. So as we can see that here we can easily compute that prediction error here is 0, and here it's going to be 10 because the difference is 10. So we can see those are the errors for each data point, and then we compute what is the sum of these losses. So according to absolute loss, the total loss for predictor number 1 is 10, and for predictor number 2 is 19. So if we're going to use absolute loss, we will have to choose the predictor number 1 as the best performing, according to absolute loss. Now, if we use different loss, for example, squared loss, the resulting values are going to be opposite. According to square loss, the predictor number 2 is better than predictor number 1. So if we use this loss, we will choose this kind of function. And then the Huber loss is somewhere in between those two. It says that predictor number 1 is slightly better than predictor number 2. But of course, for Huber loss, you have a hyperparameter that you can adjust this epsilon. So this loss is going to be dependent on this epsilon value. And I also wanted to make a distinction between prediction and inference. Well, the prediction is kind of obviously it's trying to find the hypothesis which will have a sort of best accuracy or will give the best predictions. And then if your goal is inference, then it means that you want to understand the relationship between the features or these independent variables and dependent variables or labels. It is often said that machine learning usually focus on the prediction part of the problem, while statistics, for example, focus on the inference part of the problem. And it depends what kind of question you are interested, prediction or inference, then you will maybe need to slightly adjust your approach. For example, if your goal is to really understand the relationship between features and label, and maybe to model some phenomena or some process, then you will need to put a bit more thought in the use of this linear regression, because there are some assumptions for this kind of linear model, and you would need to usually check these assumptions after you fitted your model. Some of the assumptions are, for example, that, as I said, like y, the response variable, is a real number, it's a continuous. Then you need to maybe check if the features and labels are have approximately linear relationship. If they have non-linear relationship, then this model that you are fitted, it's not going to really reflect the relationship between x and y. Then there are also some more assumptions like that these y values, or like these observations of samples, they are independent, and this additional term, the error term, is normally distributed with the mean 0 and constant variance sigma squared. So here it details that doesn't matter. Sorry. It just you just need to decide if you really want to establish the relationship between x and y, then you will need to do more thorough research in the assumptions and to use more statistic-like approach. Then if your goal is a prediction, which is what usually in machine learning we do, people usually don't do any like thorough checkups of the data before they apply some model. So this is it for the theory part. Do you have any questions considering this part? So if you have, please ask now. Okay. So now let's. So one question is, I didn't get the difference between red and black predictors. Yeah, I was I thought that this figure may actually confuse you more than explain, but let me try again. Yes, I guess the confusion comes from the colors. I should be choosing the different one. So you mean this part, right? You don't understand these subplots. So here I combined like two plots together. So these black dots are illustrate the loss that are computed for the predictor number 1 for this one. So those are the losses that are computed for each data point for predictor number 1. The red one are the losses for each data point that are computed for predictor number 2. So we have, I think, like 10 data points, and we have here 10 of the black data points and 10 of the red ones. Okay, yeah.